Hello, am I audible? Can you just let me know whether am I audible or not? Hello, hello. So we can just wait for 2 to 3 minutes more and then we can start the session. Let me see if any other participants are joining or not. So we can start from 6:10. Yeah, we can start from 6:10 onwards. Just see. Sort of, can you just let me know whether am I audible to you or not?
Yes, sir. You are audible.
Okay. Okay. Sure. So the screen is visible, right?
Yes, sir.
Okay, so we can start the session then. So, good evening, everyone. Myself, Arka. I'm working as a Prime Minister's Research Fellow in the Department of Electrical Engineering, IIT Patna. And I'm your NPTEL PMRF PA for this course on discrete time signal processing. This course is offered by Professor Mithunjay Chakraborty, who is a professor in the Department of Electronics and Communication Engineering, IIT Kharagpur. So this is the week 9 extra live session. So as I already had mentioned in my previous live session that in each and every session, I basically take one particular week's quiz and then I solve it after you get evaluated. So by that logic, I had covered week 7 solution, and today I will be taking the quiz 8 solution, and followed by that will be solving some practice questions. That is therefore throughout the course. So I will be trying to cover the questions ranging from the basic signal system, then DTFT, DFT, FFT. Majorly, I will be focusing on the Z transform, DTFT, DFT, and FFT parts. And rest of the things already in the course website also, and in my live session and in the original lecture videos also, they have been elaborately covered. So let us start today's session with this note that will be first taking the week 8 quiz solution, followed by some practice questions, which will be covering the aforementioned topics such as Z transform, TFT, DFT, everything like that. And some miscellaneous topics will also be there. So I have taken some questions which have some merged effect of combined effects of, for example, multi-rate signal processing and then applying DFT. So we'll see as okay, time goes on. So we'll see. So, so in week 8, the main topic was FFT. However, I have seen that the questions were kind of miscellaneous, which covers circular convolution. Then some questions are there which basically uses FFT, and some basically focuses on DFT and its properties, basic properties. So, so we'll let's just take up the first question. So the first question says that a sequence x of n is of length 32 given, and it is required to compute the 32-point DFT as because the length of the signal, the n is 32. So it is quite obvious that your DFT will be the same number of you have to compute the same endpoint of DFT that is there in the original signal. So 32-point DFT by using FFT and decimation in time algorithm. So we need to compute the DIT FFT. In bit reversal order, form the data vector at FFT input. So position X of 26 will be at. So we have seen while making the butterfly structure, we had seen, for example, this is a 4-point the DIT FFT. So in the last class, we had seen that this had these kind of structures. So even though at the output side it is x0, x1, x2, and x3, the output side it was following the particular order. So the indices are arranged in an orderly fashion. However, at the input side, we had seen that the input sample sequence is messed up. So, for example, over here it was so let's say x0, x1, x2, and x3. So over here, as because this is a very small problem, so I just use the property that will take up the even components in one section and will take up the odd components in the one section, and then we'll arrange it accordingly. So this is the input sequence that will be feeding into the DIT FFT algorithm. So originally the sequence had this particular sequence, for example, x naught, x1, 2, and 3. However, now you can see that the fashion that you are inputting the data into the DITFFT algorithm, that is totally different than what is there in the original sequence. So kind of the sequence order is messed up. So we need to have some strategic idea by which I will be able to know. So where will be the x1 will be positioned. So we need to identify the position of these each and every sample values at which particular location we need to feed it into the DIT FFT algorithm. So as because it is a 4-point DFT, it is very easy to say that, okay, I will group the even sequences and odd sequences, and then I will feed it into the DIT FFT algorithm. However, the problem arises when the number of endpoint DFT, so the n when n increases. For example, you need to compute 124 point DFT, 2048 point DFT. So for that particular problem, it is very problematic to identify that at which location the sample will be placed. So for that, we had an algorithm called bit reversal order technique. So in this technique, what we do is that we'll take this position 26, and over here the n is equals to 32. So as because DITFFT we are already in the last class I had told you that this is a radix 2 we are using the radix 2 method. So 32 point DFT, I can use it in the radix 2 format, for example, 2 to the power 5. So we need 5 bits of data to represent the positioning of the input sequence. So given this 5-point uh, bit information, so it will be B4, B3, B2, B1, and B0. So we need to have the binary representation in this particular fashion, and then we'll see that where the where the position of this 26 sample will go. So let's just convert into the binary representation. Now it is in a decimal representation. 11010, and this will be of binary as because it's the binary representation is basically by using 0 and 1. So the suffix will be 2 1. So over here, we'll be doing the bit reversal. So bit reversal. So we'll just do the bit reversal technique in this version. So 0, 1, 0, 1, and 1. So this is still in the binary format. So given this bit reversed order, now I will convert it into the corresponding decimal representation. So corresponding decimal representation will be 0, then to power 3, then 0, then to power 1, and then to power 0. So it will be 8 to 1. So 11. So over here, we can see that x of 26, it will get the position 11. So option D is the correct option for this particular question. So in the next question, they have been given that there are two sequences, xn and hn, and these two are circularly convolved to produce yn. So yn is equals to xn, and then convolution, this is circular convolution with h of n. So already we had seen that how to calculate this circular convolution. So circular convolution has another property that length of output is equals to maximum of length. So this len is sorry, this len of this is an operand. So this is just the same as the MATLAB command. So we'll be just calculating the length of the signal or length of any time series. So over here, x of n, comma, length of x of, sorry, this is h of n. So we'll be actually considering the length of output will be this. So over here, it will be max of. So here the number of samples that is basically xn comprise, that is 1, 2, 3, 4, 5, and over here also 1, 2, 3, 4, 5. So this is just max of 5, 5. So the lengths are just equal. So length of the output will also be 5. Okay. Now, given this into consideration, so let us just compute the circular convolution. So 1, 2, 3, 4, 0, and 1, minus 1, 0, 0, 0. So I will be multiplying each and every bit with the of xn with hn, and then for the next component I will just shift it into the right hand side, and then I will just again do the multiplication, and at the end I will add it. So 1 will be multiplied with each and every element of xn. So 1, 2, 3, 4, 0, followed by minus 1 will be now multiplied. However, I will do a right hand shift over here. So it will be minus 1, minus 2, minus 3, minus 4, and 0. Then I have 0 over here. So 0 will also be shifted 0, 0, 0, 0. So total 5 and 0, 0, 0, 0, 0. And then again shifted 0, 0, 0, 0. Okay. Okay. Now what I have is that I will just add up all the values. So it will be 1, comma 1, then again 1, 1, minus 4, 0, 0, 0, 0. Now, as because we have seen that length of the output should be 5 only. So what I will do is that I will first consider the first 5 samples. So 1, 2, 3, 4, 5. And I can see some of the samples are left out. So what I will do over here, these are 0. So as because these are 0, I cannot, I just ignore these components, and then I can just declare, okay, this will be the result. But in practice, what we do is that keeping this 5 bits fixed, as because we know the length of output is 5. So what I will do, I will keep this sequence fixed, and then I will add this thing with this particular 5 sequence, 5 length sequence. So here it will go 0, 0, 0, 0. And as because there is nothing, we'll consider here also the value is 0. And then I will add it up, and then I will get the final answer. So which is this. So keep in mind that for this particular question, as because there were 0, so we could have ignored these samples, as because we know that adding these components with 0 will yield the same result. However, the main thing is that if some values are there over here, so it will go, it will be appended after this particular sequence, and then we'll add all the samples, and then whatever is the result, that will be your final answer. So for this particular question, this is the final answer. Now the next question is in question 2 above, if xn and hn are subjected to left and right circular shifts respectively by 2 points each to produce x dash n and h dash n, then circular convolution between x dash n and h dash n will be given by, these are the 4 options. So main theme is that y of n is equals to x of n, and then it is circularly converged. So xn circularly converges with h of n. So if I just take derivative of this, so it will be y of k, xk, and h of k. Fine. Now it has been said that uh, x of n is having left shift by 2 and h of n is having right shift by 2 unit. So if uh, and they produce x dash and h dash and respectively. So if I take the DFT of DFT of h, sorry, uh, okay. So if I take DFT of h dash n, so I will get h dash k, which is basically the right shift by 2 units. So right shift by 2 unit means these are basically the circular shift. So over here they have mentioned this is not just a simple linear shift, this is a circular shift. So over here h dash k is basically e to the power minus j 2 pi r into k divided by n multiplied with original DFT of Hn, which is Hk. So Xn has DFT of Xk and Hn has DFT of Hk. So this is what comes from the intuition of the circular shift that is basically covered in, I guess, week 3 or something. So over here, this is what is h dash k looks like, and at the same time, this is right shift. So this 2 unit, let us just consider r is equals to 2. I'm just considering a generic equation, so you can just place 2 in. You can just substitute 2 in place of r over there. And here, when xn is left circular shifted by an amount of 2, it produces x dash of n, and the corresponding DFT, if I take, it will be x dash of k. So this will be just DFT of x dash of n. So it will be x dash of k. So it will be e to the power j 2 pi r k divided by n and followed by x of k. So this will be equation 3 and this will be equation 4. Now, okay. So circular convolution, now what we have to do is that we need to compute the circular convolution between x dash of n and h dash of n. Pretty fine. Now, if I just use the frequency domain contrary representation. So any sequence can be converted into frequency domain contrary representation, and that from the frequency domain representation, I can just take the inverse back to get the time domain representation. I guess someone is joining. So given this particular representation, if I just take DFT, so on the context of DFT, we know that if there is circular convolution in the time domain, then I will get in the DFT domain, there will be a multiplication. So let me just call it yn is equals to this. So y dash k will be equals to x dash k multiplied with h dash k. Okay, so I think I just need page. So y dash k is equals to x dash k multiplied with h dash k. So over here, if I just replace the corresponding representation, uh, uh, it will be e j 2 pi r k by n multiplied with x k, and here it will be to the power minus j 2 pi uh, k r by n and followed by h of k. So these two will cancel each other. So it will be xk and multiplication of h k. So this was y dash k. So now if I just take the I DFT in both the sides, I DFT, so it will give me y dash of n is equals to xn convolved with hn. So xn convolved with hn is what? In the last question, they are referring to question 2. So let me just go back to question 2. In question 2, it has been stated that two sequences have been given xn and hn, and they are circularly convolved to produce yn. So therefore, yn is basically the circular convolution between xn and hn. So therefore, y dash of n is equals to y of n. That means x dash n, if I circularly convolve with h dash n, which have been circularly shifted with the right and left shift by an amount of 2. So the convolution, circular convolution between these two sequences will yield the circular convolution between the original sequence. So thereafter, the final answer for this particular question will be y and n. Now, the next question states that a system accepts endpoint sequence and say xn. Okay, the system accepts an endpoint sequence xn. So the input is xn and carries out the circular convolution of xn with a built-in endpoint sequence hn. So over here, the system is like this. We have an hn. Issue with this 10. I don't know what is happening. So this is h of n, and we are providing an input x of n, and the output is basically circular convolution between these two. So we need to find some of the properties of this particular system. So linear shift and variancy we need to check. Now in the question, mind it, probably on 24th you guys have the exam. So mind it, this shift invariance, if it is written, so this means that it is a linear shift invariance. And if they have explicitly mentioned that whether this is a circular shift or something, so they will mention it over here itself. For example, they have mentioned over here it is a circular shift invariant or not. So if it is simple shift invariance is written over here, so you need to consider that this is not a circular shift invariance here. This is just a linear shift invariance they are asking about. So we need to see whether the system is linear or not, and whether the system is linearly shift invariant or not, or circularly shift invariant or not. We need to check the possibilities. So in the first part, let me just check the linearity property. So the first component will be linearity check. So let us just check for the linearity. We have already seen that how to check the linearity. We'll take two sequences, x1n and x2n. We'll be providing these two sequences as an input to the system. Then we'll check the output. Then we'll take the combination of this input, for example, C1x1 and C2x2, and then we'll feed it to the system. And then we'll check that whether the output of the system basically obeys the superposition theorem or not. If it obeys, then very well we can say that the system is linear. And if the system doesn't obey the superposition theorem, so then we can comment that okay, the system is not linear, it is a non-linear system. So given x1n as the input of the system, so the output y1 of n will be equal to x1n, and there will be a circular convolution with h of n. So the built-in sequence will not change, as because the system has built-in sequence h of n, so it will not change. And when x2n is provided as an input, so output y2n is equals to x2n convolved, circularly convolved with h of n. Now, if I take the DFT representation of both these outputs, so it will be y1k is equals to x1k multiplied with hk, and y2k is equals to x2k multiplied with hk. Fine. So we have checked what will be the output at an individual case when we are feeding the input one by one. For example, if I feed x1 at a particular interval of time, and if I feed x2 at particular interval of time, so the outputs are basically y1 and y2 respectively. Now I will be using some combination. So for the combination, so this is h of n, and over here I will be feeding c1 x1n and c2 x2n. Then I will see that what is the output. So let me go to the next page. So y3n will be equals to c1 x1n. Sorry, so it's a linear combination. c2 x2n, then a circular convolution and h of n. And if I just take DFT, then the DFT will be what? DFT will be y3k is equals to c1 x1k c2 x2k, and this will be just a simple multiplication. Over here it is n, so h of k. So now if I just break it, open the bracket, so it will be c1 x1 and multiplication with h of k, and then it will be c2 x2k and multiplication with h of k over here. So if I just now take IDFT, so it will be what? Y3n is equals to C1 X1n convolution, and this is circular convolution as because we are taking IDF. So this will be H of n and then C2 X2n circular convolution with H of n. So we can see both in the time domain and in the frequency domain, the system obeys the superposition theorem, and the, as the system obeys the superposition theorem, so obviously the system has to be a linear system. Okay, so next part is we need to check the points. So we have just checked the linearity part. Now we have to check the shift invariance or circular shift invariance. So for checking the shift invariance part, let me just consider when yn is circularly shifted by an amount of r, then the DFT representation will be, or let us start with the circular shift representation of xn. So let me first do a circular shift of x of n. So when I am shifting the x of n in a circular shift fashion, so the output is basically xn. So xn by using circular shift becomes x dash of n. So if I take DFT of this, what will be the output? It will be x dash k is given as e to the power minus j 2 pi r k divided by n, and it will be multiplied with the so it will be multiplied with the x of k over here. Now, given this uh, as the input of the system, if I just now consider the output of the system, that will be y dash of k is equals to x dash of k multiplied with h of k. As because we know that the system basically yields the output as a circular convolution, so I am just directly taking the DFT so that I am getting the multiplication of the individual DFT. So over here, y dash of k is equals to e to the power minus j 2 pi r k divided by n, and then it will be x of k over here. So given this uh, and multiplication with h of k, so I can write it as e to the power minus j 2 pi r k divided n, and this will be nothing but y k. So now if I just say if the original output was yk, as because yn is equals to xn circular convolution with hn. So if the original output was y of k, and if I had to take a circular shift of y of n, it will be same as what is yk is yielding. So that is basically e to the power minus j uh, 2 pi r k divided by n multiplication with y k. That means if I just take the circular shift of the original output itself, I will get the uh, representation that is basically shown over here. So the system that yields that the system is circular shift invariant. So that means once I will circular shift the input, and then I will check what is the output, and then I will uh, do the circular shift of the output itself. And then if I check that these two basically results are yielding the same representation, then I can say that given the circular shift at the input side or at the output side, they are basically producing the same representation. So that means the system is a circular shift invariant system. So the option is this one. So the system is linear indeed, and this we have already seen that is circular shift invariant system. So now we'll be moving to the practice questions. So for practice questions, I have not made these slides. So on a quick run, I will be writing the questions first, and then on hand to hand, I will be solving the answers also. So let me just write the first question over here. So the question says that we have an h of n, which is defined as, so the definition is minus 2 root 2 4 root 2 0, and the range are given as 0 otherwise, and then n is equals to plus minus 1, and then over here n is equals to plus minus 2. Now this is a system unit impulse response h of n, and the input is basically e to the power j n pi upon 4. So we need to evaluate yn equals to how much. So can anybody tell me that how to proceed for these kind of questions? So this question I have taken, this has some similarity with uh, week 1 and week 2 concepts. So can anybody tell me that how to proceed with this particular question? Anyway, I will be solving it, but day after tomorrow, you guys have the exam. So you can just unmute yourself, and if you have any suggestions regarding this problem, how to proceed, you can just tell me. Okay. So let me give you the hint. So solution. So in week 1, I will be giving the link in the I button over here. So in the week 1 also, we had seen some of the theoretical concept regarding these particular questions. So this sequence is basically called an eigen sequence. So given an eigen sequence as an input to a system, so obviously the system output is basically the convolution between the impulse response or the unit sample response and the input. So I can just readily write it as h of n convolved with x of n. So where the x of n is given as e to the power j n pi by 4. Okay, so let me just take this pi by 4 as omega e to the power j omega n. So you might now get the idea that how to proceed with this question. So uh, you need to have the relations basically on the tip of the tongue. So given this eigen sequence, you just need to answer that, okay, so it has this particular form. So yn will be some eigen value multiplied with corresponding eigenvector, as because this is an eigen sequence. So the eigenvector is the signal itself. So that is e to the power j n pi by 4, and eigenvalue is the DTFT. So let me just prove it to you how I am proceeding to this conclusion. So this will be r equals to minus infinite to infinite, and hn, let me just change the variable to h of r, and this will be x of n minus r. So if I just proceed with this convolution, so it will be h of r, and let me just take it e to the power j omega n. So it will be e to the power j omega n minus r over here, and r is running from minus infinite to infinite. Therefore, I'm not writing it again and again. So this will be h of r e to the power minus j omega r followed by e to the power j omega n. Now I'm just breaking it to two parts. So this thing is basically your DTFT, and this thing is your original sequence xn itself. So that means this is the eigenvector, and this is the corresponding eigenvalue, which is basically multiplied with the eigenvector. So y of n is equals to summation h of r e to the power minus j omega r and multiplication with e to the power j omega n. And obviously, as because they have already provided omega is equals to pi by 4, we need to substitute the value as pi by 4. So that I will do it in later. So let me just So let me just first find out what is the DTFT of this particular sequence. So the sequence is also given. So now we can compute the DTFT. So DTFT h e power j omega is equals to summation h of r is running from minus infinite to infinite over here, and then e to the power minus j omega r, and h of n, it is given as h of n, they have given us as minus 2 root 2 del n minus 1. So this is basically lying at two positions, which is at plus 1 and minus 1. So I have written the component which is basically residing at plus 1, and then I can just take the contrary position n plus 1 like this. And similarly 4 root 2 and then n plus 2 and 4 root 2 delta n minus 2. So this is this component is residing at the right hand side, and this component is this 4 delta n minus 2, this component is residing at the negative side in the sample space. Okay, so given this representation, let me just find out what will be the corresponding uh, DTFT representation. So h e power j omega, and omega, they have been given that it is at pi by 4. So let me write in more elaborate fashion. So it will be h of r e to the power minus j pi by 4 and r. Now I will be multiplying each and every location where this particular sequence is belonging, and then I will start adding up all the representations. So let me just take another page. So it will be h e power j pi upon 4. So the first component I can write it as minus 2 root 2, and as because this is resetting at delta at n equals to 1 and minus 1, let me start with the value at value at 1 itself. So it will be j pi by 4, and the second component will be 2 root 2 into e to the power minus j pi by 4, and as because I will be multiplying a minus 1 over here, so it will be converted to plus pi by 4. Followed by that, I will be having 4 root 2 e to the power minus j pi upon 2. Now, as because there was pi by 4 and I will be multiplying a position index of 2, so it will be j pi by 2. And so if you are not getting, so I am just considering this relation. So let me just copy this for your reference. So this is the relation that I am following. So I'm following this particular relation to get this. Okay. And another point is resetting at what you call at minus 2. So for that, it will be j pi by 2 itself. So over there, I will be putting minus 2. So minus 2 will minus 2 will cancel each other. Yes. Now, if I just simplify the equation, so it will be minus 2 root 2, and we know e to the power I theta is equals to cos theta plus j sin theta, and e to the power minus I theta is equals to cos theta minus j sin theta. So using these particular relations, it will be 1 upon root 2 minus j 1 upon root 2, and then the second part will be 1 by root 2 plus j 1 by root 2, and then it will be 4 root 2. I'm just merging these two results at a whole, so it will be 0 minus j and then 0 plus j. So this component is 0 itself. Then if I just take the second component over here, so it will give me minus 2, and then the components will cancel, and then it will give me plus 2 minus 2 minus 2j over here. So these two again cancel each other, so output is minus 4. So the DTFT output is minus 4. Now we can finally write the output yn was the governing equation for yn was this one. So let me just copy this part. So if I place it over here, it's fine. So if I place it over here, so the governing equation is this. So the output yn. So for this we have found out h e power j pi by 4. We have already found out what is the result, that is -4. And this will be just e to the power j pi by 4 and multiplied with n. So over there, the output will be yn is equals to -4 e to the power j pi by 4n. So this is the final output. So question 1 is done. So this particular question had two concepts. One is the eigensequence, and from the eigensequence, how to the eigenvalue was the DTFT. So we need to calculate both DTFT and we need to use the concept of eigensequence itself. So either you can just get down to the final form directly. Otherwise, if you cannot remember, you can just quickly exercise the relation, that is what is the output of the convolution in actual, and then you can get to the final answer. So question 2. So question 2 is given as x e power j omega is 1 minus 1 upon 3 e to the power minus j omega divided by 1 minus 1 upon 4 e to the power minus j omega 1 upon 8 e to the power minus j omega. Okay. So find x of n. So for this particular question, can any one of you just tell me how to proceed? So we have been given a DTFT. Find it. We have been given a DTFT, and from this DTFT representation, we have been told to find the time domain sequence. So can anyone tell me that how to proceed for this particular question? Okay, so let me give you the hint. So you can actually proceed with the ETFT itself. However, I find it bit difficult. Not bit difficult. It becomes very clumsy if I work with e to the power j omega thing. So for the sake of simplicity, I will substitute z is equals to e power j omega, and promptly I will be converting this DTFT into Z transform. So this will be x of z is equals to 1 minus 1 upon 3 Z inverse, then 1 minus 1 upon 4 Z inverse, 1 minus 1 upon 8 Z power minus 2. So from this I can start solving. So it will be 8 Z square minus 2Z plus 1 divided by 8 Z square, and over here it will be 3Z minus 1 divided by 3Z. Okay. So 1Z will be cancelled and it will be x of z is equal to 3z minus 1 divided by 8z square minus 2z plus 1, and there will be a factor that is 8 upon 3, and there will be z over here. So let me tell you a trick. What is the catch? Many of the people, what they basically do, it is they can start doing this thing: a divided by some factor, b divided by some factor, and then they start solving the rationalization part. But when z comes in the numerator part, it is always better to transfer this z to this side. So I will be writing xz upon z, and then I will start. Then I will actually start doing the rationalization. So it will be, if I just multiply, if I just take z over this side, and then it will be 8z minus 8 by 3 and 8z squared minus 2z plus 1. Otherwise, you can do it. That is not an issue, but it has been seen that in many of the problems, if you just follow this particular process, you will end up to the result very quickly. So now I can do the factorization. So it will be a divided by, so this factor will be 4z plus 1, and b will be how much? It will be 2z minus 1. 2z minus 1. If I just factorize it, it will be 4z plus 1 and 2z minus 1. So this is what I have factorized into two particular segments, that is a divided by this and b divided by 2z minus 1 over here. So I can now calculate what will be the value of a and b. So I need to find out what is the value of a and b. So for this value, finding the value of a and b, also people uses different techniques. They use what we call the cross multiplication, and then they solve the simultaneous equation. So there is also a shortcut method. So it is not a shortcut. We basically use the residue technique. So in the residue technique, the uh, transfer function is getting singularity at these particular locations. So for this one, when I'm considering a, the transfer function is getting the singularity because of this particular term, and at the location which is basically residing the location of pole, that is minus 1 upon 4. So to evaluate the value of a, I will be multiplying 8z minus 8 by 3 divided by 4z plus 1 into 2z minus 1. I will multiply with the same factor which associates with a, that is 4z plus 1, and I will be evaluating the value at the corresponding pole location. That is, if I do, if I find out the pole location for this, this will be 4z plus 1 equals to 0, so z equals to minus 1 upon 4. Now, if you just solve it, you just need to substitute the value and you will get the final answer. So for this, the final answer is, I'm just writing the answer 28 by 9. You can just exercise it by your own. So 8z minus 8 upon 3, and again 4z plus 1, 2z minus 1. Now associated with the b, the factor is 2z minus 1, for which this particular representation is getting singularity. So, and the singularity point is 1 upon 2. So these two will cancel each other, and it will be your 4 minus 8 upon 3, and then it will be 2 plus 1 over here, and then it will be, so it will be 4 by 3 and 3 over here also, so 3 3 9. So b will be 4 upon 3. Fine. So x z upon z, if I just now use the values, so 28 by 9, and then 1 by 4z plus 1, and over here it will be 4 upon 9, 1 by 2z minus 1. Now you transfer this z in this, but you just cross multiply. So now it will be xz is equal to how much? 28 by 9 z, 4z plus 1, 4 by 9 z, 2z minus 1. Now given this, let me take you to the Z transform form. So Z transform, we basically try to see it in terms of Z inverse. So it will be 28 by 9, and then I will just take Z common. So it will be 1 plus 1 upon 4 Z inverse, and then 4 upon 9. So it will be 1 divided by 1 minus half Z inverse. Now what I will do is that I will take inverse Z transform. So if I just take inverse Z transform, I will get the final answer as 28 by 9. This will be minus 1 upon 4 to the power n multiplied with un and 4 by n, and then I can take half n un. So this is your final answer. So if anyone just stuck into this problem, so I'm just writing the corresponding equation. So a to the power n un, if it is given, so the corresponding Z transform will be 1 minus a Z inverse. So this is the Z transform form, and I have just substituted the equations accordingly. So this is the final x of n. This is what it looks like. Okay. So very possibly you may find these kind of questions like how to transform a DTFT to time domain signal, or the convolution outputs, like, so you may find these particular problems to be useful for the final exam itself. Okay, so let me go to our next question. Next question is a bit easy. So x e power j omega is 1 0, and the range is given as omega c, omega, then omega c. So we need to find what is your x of n. So they have given, again, they have given a DTFT, and from the DTFT we need to find what is the time domain sequence. So if I just draw it how it looks, minus omega c, this is omega c, this is in terms of digital frequency, and this is practically this is x e power j omega mod, but uh, in if I just not take the strict sense, we can write contrarily x e power j omega mod x e power j omega plus system. So ideally, you should take a mod because complex number contains both real and imaginary, and to get the magnitude spectrum, you have to take mod. Otherwise, you can just use x e power j omega also. So to find x of n, I will be referring to the uh, equation that is the inverse DTFT form. So that is minus pi to pi x e power j omega, and let us consider pi is residing over here, and e to the power j omega n, and as because we are trying to get the sequence, so we'll be taking the integration in terms of omega. So that is why I've used d omega. So 1 by 2 pi minus pi to pi. Now here you need to focus a bit. That is For this particular region, the value is 0. So we can just write it minus omega c to omega c. Fine. And then the value is 1 at those locations, and e to the power j omega n d omega. If I just now solve it, it will be e to the power j omega n divided by j n, and it will be minus omega c to omega c. So if I just solve it, uh, just let me take 2 pi j out. It will be e to the power j omega n minus e to the power minus j omega c. Now, if I just write e to the power j omega cn minus e to the power minus j omega cn divided by 2j. I'm taking this 2j inside, and let me just write pi outside. So, and over here, I just missed this n. So it will be omega c, and over here it will be minus omega c. So uh, this I can take it as uh, e to the power. So over here this is omega c and j omega cn minus e to the power j omega cn 2j 1 upon pi omega c. So this is nothing but sine omega cn divided by pi omega c. So this is what is the final output. So in contrary, if I just tell you a very good feature of Fourier transform, be it in discrete domain or in the analog domain, if any sequence is band limited in either in time domain or frequency domain, let us consider it over here. The output is band limited in the frequency domain. The corresponding time domain will be infinitely spreaded. This is a sink. Let us consider this is just a sine, and this is attenuated with this particular factor. And you will see, if you use MATLAB, you will see that the sequence will be spreading from minus infinite to infinite. That means whichever output is uh, band limited in time, band limited in frequency, that is widely spreaded in the time domain. That means whatever response you find it in frequency domain, the opposite characteristics will be replicated in the time domain. This is called time frequency dilemma. Later in signal processing, you'll see the applications of these things very well. So let me just restrict myself to the problems itself. So another question is that let us consider xn is given. So these questions that I am taking, these have been appeared in mostly in gate examination. So from there I have actually taken the question. So it will be uh, xn is basically passed to two transfer functions. One is having the form like 1 minus 0.4 Z inverse, 1 minus 0.6 Z inverse. And the second one which has H2 of Z and output is Yn, small yn. What will be the form of H2Z such that Yn is unit delay of x of n. This is very simple question, yet this have been uh, came to get examination. So can you just tell me, this is very easy question. So you have been given two systems, which one is having h1 of z, another one is h2 of z, and the output is y of n. So what is the expression of h2z such that the output is just an unit delay of the input? That means if I more simplify the line, so yn is equals to x of n minus 1, just a unit delay of the input. Just try to find out what will be the answer. And then I will be solving it by myself. But as because you guys have exam day after tomorrow, so let's just hand it over to you first. Saurabh, are you writing the exam or not? Yeah, Saurabh. Saurabh, can you hear me?
Yes, sir.
So are you writing the exam?
Yes, yes, sir. Sir, what will be the pattern of the paper? Any idea, sir? Just
Yeah,
give some.
yeah, just it.
tips.
So we also
So
don't
mostly
know
the
that
question
what
will
will be.
be MCQ type.
Probably mostly the question will be MCQ type. Some of the question will have, I guess you have to write the answers. For example, NAT type, numerical answer type.
Okay, sir.
Uh, but predominantly it will be MCQ, I guess, because when we used to write the NPTEL exams, it was MCQ, a bit of MCQ and NAT. But currently, I also don't know what is the pattern of the question. So you can just expect you'll get more of the MCQ and some of them the questions NAT.
Any reference book also needed, sir, or most of the assignment and your video questions are enough for the exam?
Actually, frankly speaking, I also don't know that. Actually, we are not setting the question papers. We are just doing the TA sessions only. Apart from the TA sessions, we actually don't have any information regarding the final exam.
Okay,
So
sir.
probably
Thank you.
you just need to see some of the. What I would suggest is you can check the gate questions. That will be helpful because in gate you will see that from DSP very nice questions have been framed, so you can check it out. I would say gate questions you can check it out. Otherwise, there are several books are also there. Alan Oppenheim, so that book is also very good. You can get PDF copy is also there in the internet. The PDF copy is also there, so you can just refer to some of the questions.
Yes, sir. Thank you. Thank you, sir.
So for this question, so we have been told that yn should be the unit delay of the input. So if I just take the Z transform representation, so let me just forget about this final output. So given this particular system, what I can configure is that this is multiplication of these cascaded blocks, that is H2, sorry, this is Z, not P. So H2Z, H1Z, and X of Z. Now I don't know what is H2Z, but the H1Z information is obviously that is given. So that is 1/4 V inverse 1 minus 1.6 Z inverse and XZ. But as per the question, pi Z is equals to Z inverse XZ. So that is what we need to finally get. So how can we get it from H to Z? That is just multiplying with the reciprocal itself. So 1 minus 0.6 Z inverse, 1 minus 0.4 Z inverse. So these factor will cancel with each other. 1 minus 0.4 Z inverse, 1 minus 0.6 Z inverse, etc. So I can see these factors are cancelling with each other. And the last thing that we need is Z inverse term itself. So I will be multiplying a Z inverse over here. So that is what my H to Z is. So my H to Z is basically Z inverse 1 minus 0.6 Z inverse divided by 1 minus 0.4 Z inverse. So using that, I will get uh, Z inverse of x of z, and if I just take the inverse z transform, xn will be yn will be x of n. So for H2 of this sort, we'll get the output is of the unit delay of the input. Okay, so next question we can take up. Yeah, this would be the nice question. So x of n is equals to 1 upon 3 whole power n un minus 1 by 2 to the power n u of minus n minus 1. So what is the ROC? So to find the ROC, we need to actually get the Z transform, individual Z transform representation. So from the individual Z transform, I will get ROC1 and I will get ROC2. And then at the end, I need to get the intersection of this. So from this, what we can observe that this is a right-handed part and this is a left-handed part. Overall, the sequence is both-sided sequence. And in the week, probably in week 3, so we had dealt with the Z transform. So in Z transform, we had seen that if a signal is causal or right-sided, then the signal is anti-causal. That means only left-sided, and if the signal is basically both-sided signal, we call it as non-causal. So for these three types of systems, we had seen that what is the possible uh, criteria of the ROC. So over here, let's say you have poles in these locations. So considering from the farthest pole, the ROC will be diverging to outside. Then for the left-sided sequence, if the poles are like this, considering from the uh, closest pole, so it will be converging or the ROC will be inward. And if the poles are residing like this, for example, you have a one pole over here and another pole over here, then you will see that for both sided sequence, you will get something called an annular region, that is a ring shaped ROC. So by seeing the form that is given over here as xn, as because we can see this comprises a right-handed part and left-handed part, which basically comprises the both-sided sequence condition. So readily in your mind, it should click that this is a both-sided sequence, so I should get an annular region. So it will be something the ROC will be something of this format. Mod Z is less than A and B. So given this, if your what you call the options are like mod Z is less than A, mod Z is greater than B, mod Z is in between A, B. So you can just uh, tick it out. So you don't have to compute also. So these are some tricks that you can apply in the exam. But as far as whole solution is being concerned, let me just review the solution. So 1 upon 3 to the power n, and this is basically un. So this has the corresponding z transform as 1 minus 1 upon 3 z inverse over here, and uh, 1 upon 3 z inverse should be less than 1 to convert to follow the property of the z transform itself. So from that logic, it will be 1 upon 3z less than 1. So I can just take mod 3z is greater than 1. So mod z is how much? Mod z is greater than 1 by 3. Fine. We take next page. So the second component is 1 upon 2 whole to the power n u of minus n minus 1. So this has a very nice property. So let me just start with a generic function and then I will come to the final component. So a to the power n u of minus n minus 1. So if I just take the z transform, so z transform equation will be a to the power n u of minus n minus 1, and the signal is residing from minus 1 to minus infinity. It is readily observable that your signal is like this. U of minus n minus 1 is looking like this. So u of minus n minus 1, it starts from minus 1 and goes to minus infinity. Okay. So that is what the range will also be the same, minus 1 to minus infinity. So given this, and obviously there will be z to the power minus n. So n equals to minus 1 to minus infinity. And as because u of minus n, the amplitudes are 1, so I can just ignore it. So that means multiplication with 1, I have already done it. So z to the power minus n over here, and it is n equals to minus 1 to minus infinity. And then z upon a, and then I can take a minus n over here. Now for this, I can start writing the equation, that is, I can just break it down, the summation part. So it will be z upon a squared, z upon a cube, and like that, and it will go till infinite. And now if I take z upon a common, so it will be 1 z upon a, then z upon a squared. That means this is also an infinite DP series, and infinite DP series has this particular form, that is z upon a divided by 1 minus common ratio, that is z upon a. Given the fact that your z upon a, mod of z upon a should be less than 1. So any infinite series cannot have this particular summation relation, because infinite series may shoot up to the summation of infinite values may shoot up to infinity. So to get to this form, you need to ensure that the common ratio should be mod of the common ratio should be less than 1. Then only that means the values are decaying with the increment of this z by a. The values are the magnitudes are decaying. So therefore, if a series which has decaying magnitude, even if you have infinite number of samples, at infinite, if I take asymptotic approximation, so at the infinite it will reach to 0, and that's because of that the summation will converge. So therefore, your summation output will be z by a, then a minus z divided by a. So I can just cancel it out, and then z. And if I just take z inverse, so it will be z out and az inverse minus 1. So that means 1 by az inverse minus 1. Okay. So let me take the next page, half of n u minus n minus 1, which has this particular form, that is az inverse minus 1, and mind it, mod z, that is what we have seen. So I can just simplify it. Mod z is less than mod a. So mod z is less than mod a. So now if I multiply a minus sign, and then I will get 1 divided by 1 minus az inverse, and still your ROC will not change. So it will be z is equals to mod z is equals to minus a. So if I consider this particular relation that which was given over here, so I can see that this whole minus, okay, sorry, this I should take initially a, and then I will replace it with half. So I can now see minus half to the power n u minus n minus 1 will have this sort of z transform, that is 1 upon half then z inverse. But the your ROC will be of this sort. So we now have got two ROCs. One is mod z is greater than 1 upon 3, mod z is greater than 1 upon 3, and I can just write it as mod z less than half, as because mod of half is same as half. So therefore, the ROC will be, as because already I have shown that as because this is an both-sided sequence, you should get an annular region. So this annular region will start from half and it will end to 1 upon 3. If I just draw it, so 1 upon 3, that means 0.33, and this is half means 0.5. So the ROC will be of this sort. So the ROC will be annular region. So moving to the next question. You have been given a Z transform which is of this sort 2Z. Is of this sort 2Z, and then Z minus 5 upon 12, and then Z minus half, and Z minus 1 upon 3. So find x, this is mind this small x. Find small x 0 and small x infinite. You have been given the Z transform of a signal x of n, and now you have been told to find the x of 0 and x of infinite from this Z transform. happening with this thing? For this particular question, can you tell me how to proceed? Just give me a brief idea that how to proceed uh, for this particular question. Given a Z transform, if you've been told to find the sample values at 0 and at infinite, how to proceed? Okay, so the solution will be like this. Uh, for these kind of questions, please do not go for finding the x of n by rationalization and all. It will take up huge time, and then you might get the wrong answers also. So there is a methodical way for finding this x0 and x of infinity. These are called initial value theorem, initial value theorem, and this is called final value theorem. Final value theorem. So you just need to use these two relations and you are good to go to find the values at 0 and infinite. So in week 3 live session, what I can remember is that I had done a uh, great elaboration that how to get the relations. For example, x of 0 is limit n tending to 0 x of n, which is equals to limit z tends to infinite x of z. So I had derived that how x0 is basically limit z tends to infinite xz. So you can check that video for your reference. I will put it in the I button. So from there you can check the video. And let me just start solving this. So x of 0 is equals to limit z tends to infinite 2z z minus 5 upon 12, then z minus half and z minus 1 upon 3. Can anybody tell me that what will be the final result of this limit? Anyone? Please evaluate this limit and just tell me what will be the final answer for this limit. Yeah, please evaluate this limit and just let me know what is the final result. So this is the equation. Try to find the limit of this particular equation.
Is it 2?
It is 2. Yes, it's 2. So let me just give you a brief idea. So I will just take z out from each of these expressions or each of these factors. So it will be 2z squared 1 minus 5 upon 12z, and this will be z squared 1 minus 1 by 2z, 1 minus 1 by 3z, and then z will cancel and 2, and each of these factors will be 1 minus 0, 1 minus 0, and 1 minus 0 respectively. So yes, the final answer will be 2. That means x of 0 is equal to. Now we need to find what is the value of x of infinite. So to get the x of infinite value, so x of infinite, it will be limit z tending to 1, z minus 1, then x of z. These two formulas are very important. This is called final value theorem. So you can find this proof also in my third live session. So you can just refer to the third live session and you can find the proof also. But for the final exam, you don't have to uh, remember the whole proof, but you need to know how to make use of this particular relation. So this will be limit z tending to 1, z minus 1, and then followed by that whole relation, that is, it is copied. So this is the relation, and over here you cannot do much. Even if you put z equals to 1, 1, 1 everywhere, this particular guy will make the limit to 0, so output will be 0. And many of the cases, as because I was telling that your to employ this initial and final value theorem, the signal need to be causal. And most precisely, if the signal is stable, then it is very fine to apply these relations. And for the stable signals, in general, you should have a idea that your signal should be of a decaying nature. Any decaying nature signal is pretty much stable. That's because if we take asymptotic approximation at infinite, it will reach to 0. Then if you take the summation over all the points, your summation will converge, and as this summation is converging, then your signal is itself is stable. So, which is why you can see that if I take asymptotic approximation, that means this is called an asymptotic approximation. So at input, it may have some value, but when it goes to infinite, it reaches to some value which is very close to 0. So that is what we have achieved over here also. So that is just an intuition part. So you can use these intuitions later also if you want to explore in DSP a bit more. But as far as problems is concerned, let me go to the next problem. So let me see. Next problem. Okay. So this is a pretty simple problem. Xn has DFT of xk, then find what is the DFT of x of n plus n. This has also this question has also been asked in GATE examination. So just write out what will be the DFT of this particular sequence. Okay. And there are n points in x of n or in x of n plus n. We need to do an n point DFT. So n equals to 0 to n, and then here we have been asked to x of n plus m, x of n plus m, and then e to the power minus j 2 pi n k divided by capital N, as because it's an endpoint. Now we can see we are not able to make any kind of relations that we have been uh, seeing throughout this course, because had it been an n only, then we can have readily said that it has been a DFT of x of n. But the form is not matching. So over here I can see x of n plus m, over here I can just see n. So for these kind of questions, we need to make some adjustment. So the adjustments will be x of n plus m and e to the power minus j 2 pi n k by n multiplied with e to the power minus j 2 pi n k, sorry, it will be m k by n and e to the power j 2 pi m k by n. So effectively, I am multiplying a 1. So over here, let me write an 1 I have multiplied the 1, and this 1 I am expressing it by these two factors, and the summation is running over the same range. Now if I take n plus m and e to the power minus j 2 pi n plus m k n, and over here if I take e to the power j 2 pi m k by n, so we can see that this, now I can just replace n plus m as p e to the power minus j 2 pi p k n, and it will be e to the power j 2 pi m k divided by n. So this is what, this has some matching relation with x of k. That is, I can readily write it as x of k and e to the power j 2 pi m k by n. So x of n plus m has this sort of output. Otherwise, you can use the what you call the relation, and you can get the final value. Considering that in ESP it's a pretty mathematical course, and it's a very common case that you will not be able to remember all these formulas. So, nevertheless, if you are not able to remember the formula, you can just exercise it by yourself. It will not take much time. So we have seen several problems on the TFT and Z transform and samples, basic sample and sequence. Now let us further move to the filter part and the and more properties of DFT FFT. So next question is, let us consider h of s is equals to 2s plus 6 divided by s square 6s plus 8 is converted to a digital, or let me not write digital, uh, discrete time filter with transfer function h of z is equals to 2z square minus 0.5032 z divided by z square minus 0.5032 z plus k. The analog signal h of t is sampled at 2 Hz. To get the discrete signal, that is h of n, then what will be the value of k? So this question is also asked in date 2021. It is pretty recent question. So in this question, they have been given a analog transfer function. So as because this is the Laplace transform over here, so this is an analog transfer function, and they have been said that this analog transfer function, so this corresponds to a particular filter, that's an analog filter. That analog filter has been converted to a digital filter, that is h of z. So that means in week, probably in week 7, we had talked about the bilinear transformation and we had talked about the impulse invariance method. So in impulse invariance method, we had seen that if we have to design a IIR filter, so to create an IIR filter, we cannot just create the design of an IIR filter directly. For that, we need to create a prototype filter in the analog domain. And from that prototype filter, we need to get the time domain sequence. Then subsequently, the time domain sequence will be sampled. That means from this h of s, I need to get h of t. Then I will sample at some sampling rate, that is, for example, over here, that is 2 hertz. And then I will get h of n. And then readily, if I get h of n, that is the sequence, I can construct the Z transform and I can construct the filter transform. So this is indeed a impulse invariance method question, but generally whatever problems that I had solved in week 7, those were pretty straightforward. Now here they have played with the uh, technique of uh, impulse invariance method in a bit trickier fashion. So they have been asked to find this k. What will be the k such that the sampling frequency at 2 hertz will correspond to the h of n and it will correspond to the h of c. So in Z domain, we need to find the k. That means this k is coming over here in the denominator part. So that means if I am able to find the poles of Z domain, I will be able to find what is the value of k. So that means I need to find what is the value of the poles in the S domain. So if I get the value of pole in the S domain, I will convert it into the pole of Z domain, and then I can find the what you call the uh, uh, k value over here that has been asked. So poles at, let me change the color. So poles at S domain, it is s squared 6s plus 8 is equals to 0. So it is basically s squared plus 4s plus 2s plus 8 equals to 0. So s equals to -4 and -2. Fine. So I have got the pole locations in the analog domain. Now they have told that they are sampling this signal at 2 hertz. So we have seen that x of n is basically analog signal sampled at the time period. X of n, that is the digital sequence, is basically a sampled version of the analog signal with a sampling interval of Ts. So over here, they have been given the sampling frequency, that is Fs is equals to 2 hertz. So contrarily, we can find the Ts, that is the time interval of the sampling. So it will be 1/2 seconds. Now we have got the pole location in the S domain. So to get the pole location in the Z domain from the uh, IIR filter design, we had seen that Z is equals to e to the power STS. This S is basically pole at analog domain. So over here, Z1 will be e to the power S1 TS, and pole 2, that is Z2, will be at e to the power S2 TS. So over here we have pole at S1 is equals to -4, S2 equals to -2. So Z1 will be equals to e to the power, and TS is what? TS is 1/2. Okay. So if TS is 1/2, it will be e to the power -2. Yes, e to the power -2, and Z2 will be e to the power minus 1. So these are the pole locations. And they have been given hz. Hz is in the form of nz by tz. Numerator is also a function of z, denominator is also a function of z. And as because I am bothered about finding the value of k, I will not at all bothered about what is happening in the numerator. So dz, I can construct it as z minus z1, z minus z2. And we have been given dz is equals to z square minus 0.5032z plus k. So this is what is given. Now dz is equals to z minus e to the power minus 2 and z minus e to the power minus 1. So now if I just do it 1 upon e to the power 2, 1 upon e to the e only, and there will be a z, and the final thing will be x square and e to the power 1. So it will be e power 3. So this is what basically k is. K is e square multiplied with e, so e power 1 upon e power 3, and if I just solve it, it will be 0.05. It will be close to 0.05. So this is the final answer. So in this way, you can use the you can get the flavor of impulse invariance method, but they have uh, asked the question in a bit depth. Okay, now let us move to some questions on A50 also, or I have taken any questions of A50 or of DFT. So this is also a very good question. So DFT of a sequence A, B, C, D is equals to alpha, beta, gamma, and delta. Okay. Now consider another sequence P, Q, R, S is equals to A, B, C, D, and this is A, B, C, D, then D, A, B, C, then C, D, A, B. So AB is not together. So A and then the final component, and then B, C, E, A. So we have given a sequence ABCD whose DFT is like this, whose DFT is like this, and we have been told that there is another sequence PQRS, which we can obtain through this matrix multiplication. Fine. Now we need to find the DFT of PQRS. This is a very beautiful question. It seems that you have to do a lot of calculation, that you have been given the multiplication to do to get the sequence, and then you have to take DFT. So this is just a trap. You need to understand that from where to solve the question. So this question is also from GATE examination. I cannot exactly recall from which year, but this has also asked in GATE. So this question can be solved. Let us just take a transpose in both the sides. even if you cannot, if you don't take transpose also, you can find the solution. But as because I'm following the MATLAB convention, so it is better to do the transpose operation and then you can do the matrix multiplication. So as because I'm taking transpose, so whatever is there in the row that will come to column. So I can write it as A, B, C, D, followed by D, A, B, C, C, D, A, B, B, C, D, A. And then I'm multiplying with A, B, C, D. So you can see this is 4 cross 1, this is 4 cross 4, and this is 4 cross 1. So the effective output will also be 4 cross 1 sequence. So can you see any relation with this multiplication, either over here or over here? So now you can see initially the sequence was like this, and then the sequence is circularly rotated. You fix one sample to the initial position and then you rotate. Then you do with this, these two will come in the first indices and then you'll have the next positions. So this whole operation is basically circular convolution of between ABCD and ABCD. So this is basically the circular convolution. So you can check that you are shifting this sequence circularly, one point at a time. Once you have fixed D and then you took ABC, then you fix CD and then you take the next sample. Then BCD comes, then A is the last component. That means you have 4 number of samples in the signal, and in this circular convolution you will get 4 patterns. So that is what is happening. So these 4 patterns are creating this 4 by 4 matrix, and you are multiplying this with the ABCD in ABCD samples. So that means this is a circular shifted matrix and which is multiplied with the original sequence. So this is nothing but this circular convolution. So this is another form of writing the circular convolution. This is a metric representation. That is what we do in practical cases. For example, you have to write the code in MATLAB or in Python. So over there, we use these sort of relations. So this is nothing but the circular convolution between ABCD and ABCD. So for that, I can write that PQRS. So PQRS is basically circular convolution of ABCD with Excel. Now they have asked to find the DFT of PQRS. For example, let me consider this PQRS as YN, and this is XN, and this is XN. So YN is equals to XN circular convolution with XN. So YK, that DFT will be XK multiplied with XK. Circular convolution, when we take the DFT of any circular convoluted sequence, so for example, these two sequences are circularly convoluted to get the output YN. If I take DFT, I will get multiplication. Okay. So, had I been given the DFT of the original sequence ABCD, I am able to find out the final output or the final DFT output for PQRS. So for ABCD, the DFT is A alpha, beta, gamma, delta. So we can see this is alpha, beta, gamma, and delta. And this have been actually what we do is that in what you call the computers. So in mathematically, we are writing that xk is multiplied with xk, but in actual we do in computers xk and xk transpose. So alpha, beta, gamma, delta. So this you will get alpha squared, beta squared, gamma squared, and delta squared. Or in MATLAB, you will see that if you have to do like alpha, beta, gamma, delta, and alpha, beta, gamma, delta, if you need to do element-wise multiplication, or we call it Hadamard product. Hadamard product. So what we need to write x1n dot multiplication. So then x1. So this one will give you Hadamard product in MATLAB code. So by this you will get the final answer, that is alpha square, beta square, gamma square, and delta square. So I will do one more problem, discuss one more problem, and then I will finish it over here. So let me take another interesting problem. Okay. So this question, what I'm referring currently, it contains both the information of multi-rate signal processing and DFT. So this is a merged question. So 3234. It has DFT 12 2J 0 minus 2J. This is the DFT. Now we have been given another sequence 3 0 0 2 0 0 3 0 0 4. Find x1 8. This means DFT. DFT of x1 at k equals to 8. DFT of x1 x equals to 11 and more. And this is a real sequence. Original sequence is real sequence. This one indeed also a real sequence. So find this x1z divided by x1 11. So can you just tell me that what is the relation between these two signals, x1n and xn? This have been covered in the called week 4 or 5, I guess, in multi-rate signal processing. What is the relation between these two? Anyone? You can just unmute yourself and just tell me what is the relation between x1n and xn. Okay, so if xn is passed through a upsampling block, so I will get x of n by m, and in between two samples I will have m minus 1 zeros. So that means we have two zeros. So m minus 1 is 2, minus 1 is 2, so n is equal to 3. That means xn is upsampled by a factor of 3. So xn by, so this is the relation. So this is what we have seen in multi-rate signal processing that has been covered in week 5. Okay, so let us just find the DFT x1 k is equals to summation. I will just quickly write the equations e to the power minus j 2 pi n k divided by n, and n is equals to, so there are total 12 samples 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means n index will go to 0 to 11. Now we have been asked to find x1 of 8. That means your equation will be x1n e to the power minus j 2 pi n. Now k is 8 and n is total, n is equals to 12. N is equals to 12 over here. So effectively, this is 3 to x of n e to the power minus j 4 pi n divided by 3. That is x1 of 8. So x1 of 8 is equal to x of n e to the power minus j 4 pi n by 3. And it's equal to 0 to 11. Okay. Now, if you see the sequence that has been given over here, let me just copy it for the reference. So this is the sequence that have been given. So I will get only values at these particular locations. So this is location. So this is location or index. You can say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And rest of the location I will get 0. So multiplication of 0 with e to the power something will lead to 0. So I will not bother about that. Now let me just check for the first sequence when n is equals to 0, e to the power 0 will be 1. So it will be 3. Second thing, n is equals to 3. So when n is equals to 3, e to the power minus j 4 pi, 3 upon 3 will cancel each other. So therefore, e to the power minus j 4 pi sin n pi is equals to 0 and cos n pi when n is equals to even. So that is, so that will give you 1. So therefore 3 plus 2, and these all values are multiple of 3. So therefore it will follow the same rule. Over here I was multiplying with 3 and now I am multiplying with 6 and 9, which are basically multiple of 3. So in one case it will be the it will be 6, so it will be 2. One case it will be 9, so the uh, answer will be 3. So again it will follow the same rule. So eventually the e to the power j k pi, so this factor will be even all the time. And if this is even, so this will be 1 plus j into 0 form. 3 plus 2 plus 3 plus 4. So 3, 3, 6, 10 and 12. So your x1 8 is 12. Now we need to find what is x of 11. X of 11. I need to find. For any real sequence, any real sequence, the DFT star of k is equals to x of n minus k. Or contrarily, you can say that if I just write it like this, x k is star of this thing. So I need to find x of 11, that is x star of n is how much? 12 minus 11. So x star of 1. So I need to find what is x of 1 and then I can find what is x of 11. So x of 1 is equals to 3 plus, by using the same formula, e to the power minus j 2. Let me just evaluate. So when e to the power minus j 2 pi, I need to find for 1. And then over here it is n and total is 6. So it will be e to the power, the factor will be e to the power j n pi 6. Fine. So this will be pi 6 3, then 3 e to the power minus j pi 6 into 6, and then 4 e to the power minus j pi 6 multiplied with 90. Because already I have told that you will get values at 3, 6, 9 locations only. So if you just evaluate, you will get e to the power minus 2, 3 minus 2j plus 3 into minus 1. Just you can evaluate by yourself. I'm just writing the final forms. For example, let me just show you one. So e to the power minus j pi, e to the power minus j pi by 2. So cos pi by 2 is what? Cos pi by 2 is 0, and this will be minus j. So therefore 2 into minus j will give you minus 2j. Fine. So likewise, you can just find out the rest of the cases, and for your ease, I'm just writing the final value, that is 2j. Yeah. So x of 11 is x star of 1, and x star of 1 is what? X and x of 1 is given as 2j. So x star of 1 is will be x of minus 2j. So this will be this. Now, what have been told to us is what have been told to us, that is x1 of 8 divided by x1 of 11. So this question you can just take it 12, and if you take mod of x of 11, mod of x of 11, so mod of minus 2j, so mod of minus 2j is what? 2 only. So this is 2, and then if I just take, even if I just remove this mod sign, it will give me 6 only. So it's fine. So I think we have covered numerous amount of questions for this whole uh, course, which comprises, today we have comprised of covering the quiz 8 solution and several practice questions, which comprises different parts of the course, such as multi-rate signal processing, then followed by the DFT, DTFT, Z transform, FFT methods, and your exam is on day after tomorrow. So on 24th, I wish you all the very best to ace your exam with very good marks. So if you have any further questions, you can ask me. I will be happy to answer. Otherwise, we can stop the session over here. So I will be uploading this video for your reference. I will try to upload it by tomorrow itself, so that other people can also watch the video. And I will also upload this PPT file uh, by tonight itself. You can just go to the course website and go to the live video or live session. The tab is there, and then you will find the Excel sheet. And in the Excel sheet, there are two links. One corresponds to the YouTube link, and one corresponds to the presentation file links. You can just get to the presentation file link. I will just upload it after ending this session itself. I will upload the PPT over there. So you can just check the solutions by yourself also. Okay. So I hope there are no further questions. So I think we can stop this session over here. Thanks for joining the course, and I wish you all the very best for your